Module 1.1 Introduction to Functions. Objective 1 Determine if a relation is a function. Objective 2 Evaluate functions using functional notation. Objective 3 Finding the difference quotient of a function. Objective 4 Be able to use basic graphing techniques to graph linear functions. Objective 5 Be able to use the fixed and variable cost function to solve real-world applications. And Objective 6 Be able to use basic graphing techniques to solve the absolute value function.
Okay, in our first objective, to determine if a relation is a function, there's a couple definitions that we need. First one, relation, a relationship between two or more sets. Second definition, domain, the elements of the initial or input set, commonly called x values, or the first value in an ordered pair. Range, elements of the output set, commonly called the y values, or the second value in an ordered pair. And function is our last definition. It is a relation such that for every element of the domain there exists one and only one element of the range. In our first example, we are given four ordered pairs. The first one is 2, 3, the second one 3, 4, the third one is 4, 6, and the last one is 5, 8. The first thing that we need to do is set up the domain and the range. If you remember, our definition of the domain is the x value in every ordered pair. Remember, all ordered pairs, the first value is x, the second value is y. So in this one, the first value is 2, value is 3, the value is 4, and that value is 5. Okay, and our range is the second number in each ordered pair. So the first one is 3, second one is 4, next one is 6, and the last one is 8. Notice that in each ordered pair, 2 is mapped with 3. Notice that 3 is mapped with 4. Notice that 4 is mapped with 6. And notice that 5 is mapped with 8. Now, if you remember, the definition of a function stated that every element of the domain is mapped to one and only one element in the range. So if you'll look, 2 is only mapped with one element in the range, so 2 is good. 3 is only mapped with one element of the range, so 3 is good. 4 is only mapped with one element of the range, that's good. And 5 is only mapped with one element of the range. So all the elements of the domain are mapped to one and only one element of the range. Therefore, this is a function. All right, let's check out our second example. Again, I'm given four ordered pairs. Per our definition, let's set up the domain and the range. Our domains are the x values, which are 1, 3, 5, and 1 again, right? 1, 3, 5. There we go. And our range are the y values in the ordered pairs, and that is 3, 5, and 7. Notice, in our domain, 1 was used twice, but I didn't write it twice in the domain because I'll show the mapping from 1. And notice also in the range that 7 was used twice, but I didn't write it twice because I'm going to show the mapping from the domain to 7. Okay, so let's do the mappings. Okay, 1 goes to 3 is our first ordered pair. 3 goes to 5. 5 goes to 7. And 1 goes to 7. Now, let's look at 5 to begin with. 5 is our number in the domain, and it is mapped with 7, and it's only mapped with 7. It only has one mapping to an element of the range. So 5 is good. Okay. 3 is mapped to 5, and only 5. So 3 is a good, but 1's in trouble because 1 not only goes to 3, it also goes to 7. So 1 is mapped to more than one element of the range. Therefore, this is not a function. Now notice, I'm not worried about what happens in the range, but rather I'm only watching what's happening in the domain. 7 is used twice here, but that doesn't matter as far as a function goes. Only your domain cannot have more than one element. And once again, we're given 4 ordered pairs. So let's set up my domain and my range. My domain, again, are the x values. Remember that x and y. So my x values are 1, 2, 3, and 4. And my range is 3, and that one's 3 also, and that one's 3, so 3 is being used, and that one right there would be 4. Now let's do my mapping. So 1 goes to 3 in my first order pair, 2 goes to 3, 3 goes to 3, and 4 goes to 4. All right, now let's check and see if this relation is a function. Notice that 1 goes to only one item, and that's 3. 2 goes to only one item, that's 3. 3 goes to only one item, that's 3. And 4 goes to one item, which is 4. Therefore, this is indeed a function. Now, in example 4, we're going to take a look at a graph, and we're going to determine if it's a function. Say we're looking at a U-shaped figure here. And it's very easy for us to determine if a graph is a function or not. All we need to do is use infinite number of vertical lines. So I'm just going to draw a few here and see if there's any place on this graph where those vertical lines might touch twice. And you can see in this particular graph that there's nowhere where the vertical lines touch that graph more than once. So it's one and only one time. So this is indeed a function. Now in our second graph, let's make something that looks like maybe a circle. Okay. Now if we look here, we can draw a vertical line that touches maybe right there. So yeah, it may touch only once there, but there are places where when I draw vertical lines, there are places where that is going to touch more than once. Notice it touches once there and once there. If it touches more than once, then it's not a function. So it fails the vertical line test, and then it's not a function. All right, let's look at our next objective, which is to evaluate functions using functional notation. Okay, this time we're going to we have f of x is equal to 4x plus 3, and we want to find f of 3. So if we put f of 3 right here, I want you to notice that x has been replaced with 3. And so that's all we're going to do is in the regular function, we're going to replace x with that number 3. Just like we did here, I'm going to do it in this also. So notice that's 4x, and instead of x, I put 3 here, plus the 3. That will give me 12 plus 3, which will give me 15. And so now I have found f of 3, which is equal to 15. All right, in our next example, we're doing the same type of concept. We're going to find f of negative 2 if f of x is equal to x squared minus the 5. So I always put the f of negative 2 right under there, so it's easy for me to visualize that x and negative 2 are being substituted. So I'm going to put negative 2. Notice that when I substitute, I always use parentheses. because that keeps my sign straight. So that would give me negative 2 squared is negative 2 times negative 2, which would be positive 4 minus 5, which will give me negative 1. And so notice that f of negative 2 is equal to negative 1. And our last objective for this section is to find the difference quotient of a function. The formula for the difference function is f of x plus h minus f of x all over h. Okay. Let's use this formula in our first example. If we are given that f of x is equal to x plus 9x plus 8, we're going to find the difference quotient. Okay, so notice what I'm going to do here is first I'm going to write everywhere there's an x, I'm going to substitute an x plus h. So this is going to be 9 times, and instead of x, we're going to replace it with x plus h plus the 8. Okay, so that's got this part of it covered. Minus, now I'm going to use parentheses here because I know that minus has to go to the entire second part of this. F of x. Well, f of x is simply this. So it'll be 9x plus, here we go, all over h. Okay. Now I'm going to distribute into this, so that would be 9x plus 9h plus 8. I'm going to distribute this minus 9x minus 8 all over h. And that will give me, notice that the two 9x's are going to cancel. And notice that the 8's also cancel. The negative 8 and the positive 8, which will give me 9h on top over h on bottom. And notice that these h's will cancel, which will give me 9. And so my difference quotient will give me 9. All right, in our last example, we get to do a little more fun algebra stuff. We're going to find the difference quotient for this one. Now remember, my difference quotient is f of x plus h minus f of x all over h. So we're going to keep that in mind. All right. So now, first thing we're going to do is we're going to replace x plus h. In order to do this part, we're going to replace x plus h everywhere that there's an x in the function. So we're going to start off with 2 times x plus h quantity squared minus 3 times x plus h plus 4 minus these parentheses and put the function in there. So it'll be 2x squared minus 3x plus 4. All over the bottom, which is h. Now let's do some algebra. First I'm going to FOIL this. So that'll be 2 parenthesis x squared plus xh plus xh plus h squared. I'm going to distribute this in. That'll give me minus 3x minus 3h plus 4, and then I'm going to distribute the minus 2x squared plus 3x minus 4. Okay, and so notice that I distribute the minus in all those, all over h. Okay, next I'm going to distribute the 2, so that'll be 2x squared plus 2xh plus 2xh plus 2h squared minus 3x minus 3h plus 4 is 2x squared plus 3x minus 4 all over h. Okay. And now I'm going to combine like terms, and notice that this 2x squared will cancel with this negative 2x squared. Notice that this negative 3x and that positive 3x will cancel. Notice that I can put together these two 2xh's, which should give me 4xh. Okay, so that's taking care of those. I've got plus 2h squared here. Okay. And notice that that positive 4 and that negative 4 cancel. And I'm left with that minus 3h right there, all over h. Now, if you remember our old algebra, we had the ability to factor out things if they were in common. So on the top, I'm going to take an h out of all three of those. So that'll give me 4x plus 2h, because I'm going to take one of those h's out, minus 3 over h, and look what happens to my h's. And that's what we're trying to get done there with the difference quotient. So my difference quotient would be 4x plus 2h minus 3.
The concept. All general functions can be written and graphed using the format f of x minus h plus k, where h describes the horizontal shift of the function and k describes the vertical shift of the function. Caution. Notice that h has a minus sign in front of it, which means the opposite of h, whereas k has a positive sign. Objective 4. Graphing linear functions. A function is defined as linear if the x or the y value are of degree 1. In our function format, f of x minus h plus k, we're going to find our point of emphasis by looking closely at the k. The format for linear functions is called the slope-intercept form, y equal mx plus b. Notice that the y-intercept, or the b, will simply be the number or constant by itself, without a variable. Also notice that the slope, m, is the coefficient of x. The slope is defined as rise over run. Let's look at example 1, and let's learn how to use the slope-intercept to graph linear function. We need to remember that our slope-intercept form is y equals mx plus b. And m is the slope and b is the y-intercept. So notice that if 3 is the number that's the coefficient of x, or the number that's in front of x, then our slope would be equal to 3, and we need to write it as a fraction, so 3 over 1. Okay, and remember the top part is our rise, or the numerator is our rise, and the denominator is our run. Okay, and notice that our b is going to be equal to the number or constant that's by itself, which is a positive 2. So to go through and graph this line, we're going to start at my y-intercept, which is b. So on the y-axis, I go up to 2, and that's my first point. And then I'm going to rise 3, 1, 2, 3, over 1 will be my second point. Rise 3, 1, 2, 3, over 1 is my third point. And I'm going to draw my line. And I have now graphed the linear function. And our second function, again, we're looking at our m being negative 2. And to write that as a fraction, we're going to write it negative 2 over 1. And our b would be the constant by itself, which is negative 5. So in this case, I'm going to start at negative 5 on my y-axis. And I'm going to rise negative 2, which means actually go down 2 and over 1. So there's my second point, down 2 over 1, which will be my third point. And I'm going to graph the line. And once again, I have graphed my linear function. In example 3, once again, the coefficient of x is going to be my slope, which is m equal 2/3. But this time I don't have a constant by itself, so there is always understood to be a plus 0 out here. So my b would be equal to 0, and if you look at y-axis, that's going to end up being the origin. So now I'm going to rise 2 and run 3, rise 2 and run 3, and graph my line. Example 4, we're looking at y is equal to -3. Well, here we can write this in slope-intercept form. Notice it doesn't have an x, so we're going to write it as 0x, 0 over, and we can pick any number because any number would be equal to that, minus the 3. So notice my slope would be equal to 0, or 0 over 3, or 0 over 4, or whatever we wanted to use, and my b would be equal to -3. So here, I'm going to put -3 is here, and I'm going to rise 0 and run 3. Rise 0 and run 3. So you can see it doesn't matter what number we're going to use. And this one is a horizontal line. In Objective 5, use the fixed and variable cost function to solve real-world problems. Example, little Johnny pays $20 a month for his cell phone service and 4 cents a minute for any minutes used. Write the cost function C of x and determine how many minutes he used if his bill was $52. So in order to write the cost function for this, which will be C of x, we're going to have a variating cost of 4 cents times the number of minutes, plus we have a one-time each month charge of $20. So notice that this is the one-time charge and this is the variable charge. And this one depends on how many minutes is used. We need to find out when little Johnny's bill is going to be equal to $52. So we'll put 52 is equal to 0.04x plus the 20. Now, in this case, we need to find out how many minutes, or x, he has used in order for his bill to be $52. Okay, so we're going to subtract 20 from both sides here, and that will give us 32 is equal to 0.04x, and we're going to divide both sides by 0.04, and we're going to get x equals 800. And so, in this case, little Johnny has used 800 minutes in order for his bill to be $52 for this particular month. Objective 6, graphing absolute value functions. We need to remember that our general format when we started off with linear functions is y is equal to f of x minus h plus k, where k was the constant and notice that x minus h is within the function. So let's look at our basic absolute value function and we'll learn how to use this general format. Our absolute value function, we have a vertex at 0 or a reference point at 0, and this function is going to go like that, and it's going to go like that. So it looks like a big V. In our second example, notice that we're going to have a vertical shift because this 3 is on the outside. So this is going to shift vertically up 3. So it's going to look just like a V, except now our vertex is going to be up here. So notice we just simply moved it up 3. In our next example, notice that the number here is inside the function. And remember, we talked about how it had a minus sign, so it's going to do the opposite of what we think. It's going to be a horizontal shift. But it's going to shift left 2. Okay, so we're going to shift this left 2, and that's going to be our vertex right there, and it then has the V shape. And last, using the absolute value function, notice that we have 2 shifts here. We have a vertical shift, which is up 4, and we have a horizontal shift, which is going to be right 2. So from our center point, we're going to go right 2 and up 4, put our point of reference or our vertex, and draw our absolute value function.